morning, everybody. So today we start with Cieliebak using this course.
Okay. This is nice, huh? Good morning, everybody. I'm sorry that we have to start so early today. We're going to start nice and easy, so nothing difficult today. Yesterday we talked about the Kepler problem, and it's been known, and we derived it yesterday, that the relative motion between two bodies, if there's no other bodies, just two bodies, is on an ellipse with a center of mass in one of the focal points. And we derived that from the fact that the two-body problem is completely integrable. And you would think that then there's nothing new to be said about the two-body problem after that. But in fact there is, and I want to present one other aspect, and that is that besides we already have enough integrals of motion to have it completely integrable and to be able to solve it, but there's yet another integral of motion on top of the ones that we've seen, which are energy and angular momentum. Namely, there's the so-called Laplace Runge-Lenz vector, or sometimes called just the Runge-Lenz vector. So who of you has seen that before? Knows that? Not even you. Okay. Fine, because I can even teach the physicists some new physics here. So, this is the following. It's let's call it A. It's a vector-valued quantity, and it's defined as momentum times angular momentum. Let me get the sign right. Minus position divided by absolute value. And so let's check that this is in fact a constant of motion. So we just take the time derivative. So we have p dot cos L plus, well, L is constant, so there's no derivatives of L. And then we have minus inner product of Q with Q dot divided by, and this comes with a plus, Q cube times Q. And now we use the equations of motion, so we know that Q dot is equal to P, and P dot is equal to minus Q over Q cube, and L is Q times P. You plug all that in, and okay, let me do it. As I said, we're going to start nice and easy. So P dot is minus Q over Q cube times, and let's replace L with Q times P, and then Q dot. Wait a second, what am I missing? I'm missing one term. Yeah. We have a minus Q dot over Q. Mm-hmm. Yes.
Another thing, you are considering the L as constant.
Yes. We know already it's constant.
Yes.
Because
it's a Keper problem.
Yes, it's a Keper problem. That is constant.
Okay.
Yes, so there's no derivative of L. But of course, from this term I get two terms. I get derivative of this one, which is just Q dot over Q norm, and I get another one which I have written. So I forgot this term. Yes. So now, so what we have? So minus QP Q over Q cube, and this comes with a plus, and this comes with a minus. Like this. And now we just need to expand this guy. The triple cross product we can write as QP Q minus QQP, and the other terms just carry over. And now we see that everything cancels because we get this term which will cancel with this one, and the other two terms are also the same. Yeah? So we get 0. Okay, so this has two nice consequences. So it's yet another integral of motion. Now, a system cannot be more than completely integral, yeah? Because you can have, if the number of degrees of freedom is n, there can be at most n pairwise commuting integrals. So those are not giving us new commuting integrals. They cannot commute with the previous one, and in fact you can compute the commutation relation, and they don't commute with the other ones. But in fact they are much nicer integrals than for example, angular momentum. So for these, with this integral you can very easily solve the equation of motion. So this has two consequences. The first one is, so let's again suppose the angular momentum is pointing in the third coordinate direction. And then we can write q of t in the xy plane. So then we write it in the complex plane, in the complex plane of the first two coordinates in the planes orthogonal to L. And then, so this is the plane orthogonal to L. Now let's look at the Runge-Lenz vector. The Runge-Lenz vector, this term is orthogonal to L, and this one is also because Q is orthogonal to L. So A is also orthogonal to L, so it's in the same plane, right? So this vector lies in the same plane. Now, what do we get from that? So we can write both of them as complex numbers. So let's write Q as R e to the I phi, and A as the absolute value e to the I phi 0. And then let's multiply this equation here with Q. Take the inner product with Q, and let's see what we get. We get inner product of A with Q with the left-hand side is, let me bring, then this one gives us just norm of Q, let me bring this to the other side, is equal to P cross L times Q, which we can permute. So this is L inner product with Q times P, but Q times P is just L itself. So this is L squared. And which is just little L squared. And this one we can write as norm of A, norm of Q, cosine phi minus phi 0. Oh, yes, exactly. So the left-hand side is this one plus another R here. And if we solve, we find that 1 over R is equal to 1 over L squared, 1 plus absolute value cosine phi minus phi 0. And this is again an ellipse. So, yeah, so yesterday I had shown you that this is one presentation of an ellipse in the plane. Right? So this is much easier than using angular momentum. From this, it immediately follows. You immediately have the equation of an ellipse there, and you also see that this guy is the eccentricity. Yeah. And so it really has direct physical meaning. This Runge-Lenz vector. Okay, so this is one. So this is much shorter than what I did yesterday. But then there's another insight which we get from this. And for this, let me write it as follows. Let's compute the Runge-Lenz vector more explicitly, knowing that it's in the plane. So P has components P1 plus I P2, which is also lying in the plane. And L is L times the third vector. So let's compute the cross product with the third vector. And you compute here, so it's P1, P2, 0 cross 0, 0, 1, which gives us P2 minus P1, 0. Or I can write it as minus I times P in complex notation. Yeah? So this is just rotating P by 90 degrees clockwise. So therefore, we can write the Runge-Lenz vector. So the first term is minus I times L times P. And the second one is minus Q divided by absolute value. Let's multiply this with I divided by L. And then we get the following equation. P minus I over L A is equal to I over L Q okay. So let me discuss what this means. So the first thing we can do is, so here on the, so if we take absolute values on both sides, then P for all times minus I L over A, all these are constants, absolute value is equal to, this has absolute value 1, so it's equal to 1 over L for all times. What does this mean? This means that if you look at the motion of the momentum vector or the velocity vector, it's moving on a circle. Huh?
The second law of Keper
is it second? Well, it's not second law of Kepler. It's well, I think this was. I'll go on. So the motion of the maybe together here. So there's a vector. Let me maybe put it here. So there's I over L times A, wherever A lies. If I choose A to be on the real axis, then this is on the imaginary axis, and then we have a circle around this. And let me try to stick to my drawing. So the momentum vector is moving on that circle. Yeah? Okay. So is this not Kepler's second law? Yeah. So it's this was first discovered by Hamilton, I think. Hamilton in 1847 that if you look at the velocity vector, it's actually moving on a circle. We know the position vector is moving on an ellipse, but the velocity vector is moving on a circle. So in a way, the ancient Greeks were reivindicated here. So they wanted to describe the planetary motion by circles, and here it is. Yeah, you just have to go from the positions to the momenta. Yeah? So and we already see that. So this suggests that it might be a good idea to switch the roles of positions and momenta. We're going to see more of that later. Yeah? So because the motion in momentum space is simpler, it's just on a circle. And if we look more carefully now just at this equation, it tells us even more. If we look at the difference vector of p to the center of the circle, the vector that I drew, then this vector, because there's an I here, is perpendicular to the position vector q. Okay? So now let me try to get a decent drawing here. So let me draw an ellipse for q. Now the drawing is probably not going to come out so nice. So this should be an ellipse whose focal point is at the origin, because that is how we measure q. And then what we need to do is to find at time t, if we know the momentum vector, well, we draw the position vector q to be orthogonal to this one. That's what this equation tells us. No? And then this will be q of t. Right? So you can they are related, in fact, in a very nice geometric way, yeah? But somewhat non-obvious, yeah? Because this is the focal point, and this is the center of this circle is not on the major axis of the ellipse, but it's off by some amount. Yeah? And but then you follow the rotation of the momentum vector for every time. You just geometrically construct the motion of the position vectors.
Which is the focal point now?
This is the focal point of the ellipse. So the ellipse has two focal points, one here and one here. Yeah? And right. And so this is. I think this is very pretty. That you have this nice relation. Okay. And this, for some reason, this Laplace Runge-Lenz vector is not so well known, and it's in fact so little known that this was discovered many times in the history. In fact, it was discovered by neither of those three people who give name to it, but that's very common in the history of science, I think. And so it was, let me try to at least list the correct names. So it was discovered first by Jakob Hermann, who I never heard about, in 1710. And then Bernoulli, also around the same time, described it, and then was rediscovered by Laplace in 1799, and then it was again described by Hamilton in 1847, and then it really became popular only when it came up in relation to quantum mechanics. So then, well, there was Gibbs also who had rediscovered it, and then Runge, Lenz, and Pauli all discussed this in connection with quantum mechanics. Pauli, in fact, used this to describe his quantization of the hydrogen atom, and then it became popular. And so the names that stuck were the latest ones, Runge and Lenz. They were in the 20th century, but it had been discovered in the early 18th century already by other people. Okay, so this was one addition to the Kepler problem, and the second one is about regularization. And I'm going to discuss it for the Kepler problem, but in fact the same discussion will hold for the three-body problem. So it will be exactly the same regularization will in fact also regularize the three-body problem, and I will come to that later. So as we see, because the motion is taken in a plane, let me restrict it immediately to the case that the motion is in a given fixed plane, because it's just slightly easier. You could do the spatial one the same way. Okay, so, and the goal is to extend the solution of the Kepler problem through the collisions, because there's this unpleasant thing that the solutions, when the angular momentum is zero, and it really goes through the origin, then it means that the two bodies collide, and then the solutions don't exist. But in fact, you can nicely extend the solutions beyond collisions in a smooth way, and that I want to explain. And then that makes mathematicians happy, because then we are getting a compact space on which we can study the motion, and we don't have to take out some point and create some non-compactness. Yeah? So, and there's in fact several regularizations. I want to discuss two of them. One is due to Moser. And I'm going to start with this one. So note or recall that the Hamiltonian is given by p squared over 2 minus 1 over q after I normalized all constants to 1. And we're going, let's fix some energy level that we want to recall, that we want to look at, and I want to fix some negative energy. So when the energy is negative, they're going to move on ellipses. When the energy is positive, they're going to move on hyperbola. And this is, I'm not going to discuss that case. There's a parallel discussion for positive energies, but let me stick to the negative energy case where we have bounded motions. And so let's first consider the case c equals minus 1/2, and in fact you can reduce by rescaling to that case. Let me maybe not discuss the general case. So let me say without loss of generality, after rescaling in P and Q, you can reduce to this case where the energy is minus 1/2. And then the computation becomes easier. So then let's do some transformation of this one. Let's multiply this equation by the absolute value of Q to get rid of the singularity here on the right-hand side. So then we get p squared q over 2 minus 1 is equal to minus q over 2. Or I can write it as follows, and it is p squared plus 1 divided by 2 multiplied by q is equal to 1. So this looks like a level set of a different Hamiltonian. Now, to make it look more like a classical Hamiltonian, let me even square this again. So square the left-hand side. So then it's p squared plus 1 over 2 square times q square. Is this what I want? Yes. And let me divide this by 2 is equal to 1/2. Now this, if I denote this as a new Hamiltonian, now this is, I'm writing my Hamiltonian always as position first, momentum second. Now I want to switch the roles of P and Q, because I want to view Q as a momentum variable, because then this is just a quadratic expression in Q where the coefficient is a function of P. So this is K of P minus Q. So this I view as a new position, and this as a new momentum. And I explained yesterday that QP goes to P minus Q is a symplectic transformation. So Hamilton's equations will still take the same form. Yeah? Okay. So what we have, maybe let me not do all the computations, but this describes the free motion. It's free motion because this is a purely kinetic energy, this Hamiltonian. Yeah? This is purely a function momentum square over 2, but where the metric is not constant, but the metric is position dependent. Yeah? So it's a free motion because there's no potential term, so there's no other forces. It's a free motion, or as mathematicians would call it, it's a geodesic flow for the metric which is the standard metric multiplied by this term, so which has coefficient p square plus 1 over 2 square times the standard scalar product on R2, where R2 is the plane where our P now lives, yeah? And we view P as the position now. Yeah? Now this metric, actually, sorry, I'm wrong. This is the dual metric that we see here, so we need to dualize. I'm sorry, so the metric is actually this one. In fact. Okay. So now this metric is well known to geometers. You know it? Yeah? You are a geometer here. Uh-huh. So this is the standard metric on the round 2 sphere. Okay. So this corresponds to the standard metric on the unit sphere S2 sitting in R3. So the standard sphere of radius 1, so here it is. In R3, so the radius here is 1, under stereographic projection. So you put the plane R2 here, and you do stereographic projection. So here's our point P in the plane, and we associate to it a point on the unit sphere. Let's call this point maybe X. By this rule. Okay? So this picture defines the stereographic projection. So stereographic projection, let me maybe write it as phi from the plane to the unit sphere, which is mapping this to X. And from the picture, doing some elementary geometry, basically you look at the two parallel lines here and you look at the ratios. Yeah? Given, let me describe the map in one direction. You can work out the difference. So P1, the first component of P, is X1 divided by 1 minus x3, and the second component is x2 divided by 1 minus x3. This is how you go from x to p. Okay, and then you work out the inverse of this. Yeah. So maybe I'll write the inverse of it. So the inverse is x1 is equal to 2p1 divided by p squared plus 1. We see this expression already come up, which appears in the metric. The same for x2. Just put p2 here, and x3 is p squared minus 1 to p squared plus 1. This is the inverse map, how from p you get to x. Then you take this map which sends p to x, you compute its derivative to get the tangent map, then you plug in two vectors here, take the standard metric here on the sphere of those two vectors, and you compute for half a page, and you get this expression. So let me not do this computation. Let me just explain some things about this. I was slightly imprecise here. So this is not hitting every point on the two sphere, but it's hitting every point except the North Pole. So the E3 vector is not being hit, yeah? Because there you would have to go parallel, and then you're not intersecting the xy plane. So it's a bijection between the plane and the sphere minus the North Pole. And it's a diffeomorphism, so going both ways. So what does the Hamiltonian look like? Maybe I should not have erased the Hamiltonian. Well, it's just this free motion. Okay, so it is free motion on the sphere. So if you translate this from R2 by stereographic projection to the two sphere, then you get the Hamiltonian. So this the motion on the two sphere, or you should rather say on the cotangent bundle of the two sphere, is then described by this Hamiltonian. Which is just the standard quadratic Hamiltonian with respect to the metric on the two sphere. Yeah, which is well, let me call the coordinates here x is the base on S2 as in the picture, and then y is the fiber coordinate, and then this is described just by the Hamiltonian y square over 2, where this is the standard metric now on the sphere. Yeah? The standard round metric on the sphere. And then if you have a cotangent vector, you take the dual metric on the cotangent space and you take its norm square, and that is the Hamiltonian which describes it. It's a pure kinetic term without any forces, and it's so its solutions are geodesics for the round metric on the sphere. Yeah? You have a question? No? Okay. Yeah. So solutions are geodesics on the round two sphere. We know what geodesics on the two sphere look like. Yeah? So they are just great circles. So solutions are great circles on the two sphere, you map those solutions to the plane under stereographic projection, they go to circles. And we recover Hamilton's theorem that the momentum vector moves on a circle. Yeah? So this is another way to arrive at Hamilton's theorem that the momentum vector moves on a circle. Yeah, so they project under stereographic projection. To circles in R2. And this is where the momentum vector lives. But we also see now that here, if we look at the geodesic flow in the two-sphere, which is a priori only defined outside of the North Pole, because this North Pole does not correspond to a physical point of our system. But of course, we can now put in the North Pole, because for the geodesic flow on the two-sphere, it makes absolutely no difference whether the motion runs through the North Pole, right? There's some great circle going through the North Pole as well, and it's just nice and smooth. Yeah. So in this picture, we can insert the North Pole as a non-physical point, which we do not see under stereographic projection in our physical system. So what does it mean in the physical system? It means that the momentum or the velocity goes to infinity. Yeah? And if you think back of the original Hamiltonian, then it was that momentum, that p norm squared times q was roughly being constant. So when p goes to infinity, q goes to 0. So this precisely corresponds to collision points. So the geodesics through the North Pole E3 correspond to collisions where q of t goes to 0, and in fact the norm of p of t then necessarily has to go to infinity. So the particle moves to the origin where you have the singularity, and it's becoming infinitely fast there. And then when you work it out more precisely, then you can see what it means physically to extend the solution throughout. It means that in the plane we have the origin here, we have our motion q, which is running into the origin. And then what happens when it's hitting the origin? Well, here the solution just extends smoothly. When you work out under stereographic projection and all these transformations, what it means that the particle bounces back. So then afterwards, physically the solution would stop here, right, at the end of time if we bump into the sun, but mathematically the solution just bounces back. This is where it comes down physically. And but the beauty of it is that this is a smooth motion. It looks like there's something drastic happening here, but after you transform to a motion on the two-sphere, then nothing happens at all. It's just nicely going through. This bouncing back you can see because as you cross, from one side to the other, then the velocity vector is jumping over to the other side. It's changing sign. Yeah? So it's coming from the other side, really.
So before you regularize, you can compute that the time that it takes to get there is finite?
Well, the time is finite, in fact, yes. And so this is something which, it's a good question. So we are changing the time parameterization now.
Oh, you are changing? Changes.
Yeah, so I have rescaled the Hamiltonian by multiplying with the norm of q to make it non-singular, and then did some further transformations. So we have changed the time parameterization. So geometrically we still have the same orbits, but the time parameterization has been changed. But it is true that it's going there in finite time. Yeah? So,
Okay, so this is
you can compute that. But there's some integral and you show it's finite to get the time. But the time parameterization now is becoming different. This was actually, by the way, also true for Hamilton's theorem, that if you say that the momentum vector is moving on a circle, it's not moving with constant velocity. It's also just a geometric description of the orbit that is moving on the circle, but I'm not claiming it's moving with constant velocity. So in all this discussion, we are losing the correct time parameterization. Yeah? Okay, so this is probably what I wanted to say about Moser regularization. And now there's another regularization. No, I wanted to add one more thing about the Moser regularization. So why was this Runge-Lenz vector rediscovered so often and forgotten again? Because it's a conserved quantity, it's a vector-valued conserved quantity, which does not obviously come from a symmetry of the system. Recall that we had discussed Noether's theorem that symmetries of the system give rise to conserved quantities. And this works nicely for the momentum and for the angular momentum. They come from nice symmetries. The angular momentum comes from the rotational symmetry of the two-body problem. But the Runge-Lenz vector was a mystery. It basically came out of nothing. Yes? And that's why I think basically people just stumbled upon it by accident and discovered it. And this, then because they didn't understand what it meant, they forgot about it and it was rediscovered again by accident. Yeah? But so is there a symmetry of the problem from which this Runge-Lenz vector arises by Noether's theorem? And here now Moser's regularization gives us an answer, because note that what is the symmetry of the planar Kepler problem? Well, so we already used, in the spatial problem, we have an SO3 symmetry, because we have all the rotations in 3 space. But now we already used up some of it to say that the motion is actually taking place in a plane. So what is left of that symmetry when we restrict to the plane? There's only rotations in the plane. So there's only an O2, or let's say SO2 symmetry. Yeah? It's just rotations in the plane. Well, it's in fact an O2 symmetry. I don't know why. And, but now, after this transformation, we transformed it to the geodesic flow on the 2-sphere. Now, what is the symmetry group of the 2-sphere? Those are all rotations of 3 space. All, because they preserve the unit sphere, so they all give us they preserve the standard metric on the 2-sphere. Yeah. So the Moser regularized Kepler problem has an O3 symmetry, because this is all the rotations on the 2-sphere. Yeah? So we got from the plane to the 2-sphere under stereographic projection by inserting the point at infinity, and all of a sudden we have more symmetry. On the plane we only had rotations in the plane, and now note that we got rid of, in the plane we have more symmetry, we have translations in the plane, but we got rid of those because we put the attracting center at the origin. Yeah? So the system is no longer invariant under translations. Yeah? So it's really only invariant under the rotation. And now all of a sudden we have an O3 symmetry. This gives us rise to 3 conserved quantities, because it's 3-dimensional, to a vector-valued conserved quantity. Yeah? So this gives rise to a conserved quantity in R3, a vector valued conserved quantity, and this vector valued conserved quantity is in fact, well, what is it? It is the two components, A1 and A2, of the Runge-Lenz vector, because the Runge-Lenz vector, after we restrict it to a plane, was a vector in that plane. And we had the third component of angular momentum. Okay.
It's not a problem that you change the Hamiltonian.
Sorry?
It's not a problem that you change the Hamiltonian. There's probably some relation.
Yes, so yes, well, yes, it's a good question, because we have somewhat drastically changed the Hamiltonian by multiplying by some function, but we've done it in such a way that the orbits of the Hamiltonian system of the old one and of the new one are the same.
Okay.
Right. So if we have a conserved quantity which is invariant under the motion of the old Hamiltonian, it will be invariant under the motion of the new Hamiltonian, although we have changed it. But by the way we changed it, if you think about it geometrically, that they have the same orbits, it follows that they will also commute with the new one, with the new Hamiltonian. Yeah? So they will, so the conserved quantities of the old Hamiltonians will be conserved quantities of the new one. But for the new one, after we translated it to the sphere, we get more conserved quantities because we have a higher symmetry group. And if you take the standard rotations of the two sphere, then there's a rotation around the z-axis. Now that under stereographic projection goes to the rotation in the plane. So that will give rise to the angular momentum in the plane. But then there's the other two rotations around the x and y axis. And when you translate them back to the plane after under stereographic, it's kind of a longish computation, you know, which I'm not even trying to do. Yeah? And then you pull that back, and you'll find that it's you get the Runge-Lenz vector.
So you have things that are like linearly independent in R3, but when you project, they become linearly dependent? Is that the issue?
Yeah, this is, I mean, it's, okay, it's functions.
Yeah.
You should think of the conserved quantities as functions on the phase space. Mm-hmm. And as functions, they are linearly independent in the sense that they at every point the Hamiltonian vector fields tend to be linearly. Wait, no, this can't be. Wow.
I thought this is a commutation problem. I mean,
Yes, yes. So I think they are linearly independent, presumably, most of the time, but they are not commuting. So this is not three commuting, because, but they have the three components. They have the same commutation relations as three components of angular momentum would have, because they come from the same symmetry. So, so the commutation relation will be that A1, A2 will be A3, and so on, and cyclically. Yeah. And those actually you can check from yeah. So to prove that this pullback and so on gives you the Runge-Lenz, this is a difficult computation. But this one, I wrote you the formula for the Runge-Lenz vector and for the angular momentum. You can just compute the commutators, and you'll see that they satisfy this relation, these relations. Yeah. So they are not Poisson commuting. Yeah, because we know the system has 2 degrees of freedom, so it cannot have 3 Poisson commuting integrals. So. Okay, now the last thing I wanted to discuss now is the second regularization. It's Levi-Civita. Because this will also play a role in what I want to say about the three-body problem. So This is actually, well, it's a different idea, but we'll see it also leads to regularization. So let's take phi from C to C, the map Z going to Z square. Okay. Very harmless looking map. So this, you can think of it as a branched cover of the complex plane onto itself, branched at the origin, and 2 to 1. Yeah? So it's a 2 to 1 branched cover. It induces a cotangent map between the cotangent bundles. Let's call it phi from the cotangent bundle. Well, the cotangent bundle of C is just, you think of C as a position vector, and then you add 2 momentum vectors. So this is just R4 as a vector space, but we think of it physically as a cotangent bundle with this standard symplectic structure and variables in Q. And well, you work out. So this should map a base point Z and a corresponding momentum vector. This is a general fact whenever you have a diffeomorphism of the position, it's almost a diffeomorphism. You map it to phi of Z, and then what you take the derivative of Z, then that would map tangent vectors. Now you want to map cotangent vectors, so you take the transposed, but then it goes the wrong way, so you take the inverse. And you apply that to W. Okay, well, you compute, and you see that this comes out to be, well, this one we know, its definition, and this one we just get factor 1/2 on the right position. This becomes W divided by 2Z bar. So let's actually say we do it only outside of the origin, where Z is not 0. And so something is happening at the origin, and that's what we want, because we want to regularize collisions at the origin. Yeah? So this is your workout comes with the map. And you can check, this is always, if you take any diffeomorphism of the positions, you lift it to by its cotangent map. That's always a symplectomorphism of the standard symplectic structure. So this is always symplectic. Yeah? This is not quite a diffeomorphism, but locally it's local diffeomorphism. Yeah, it's 2 to 1, which is good enough. And now let's compute the. So here, let's say on this side, this is our original positions and momentum for the Keper problem. And then we pull it back under this map. And so here we have the standard Hamiltonian of the Keper problem. And now let's put it back under this map and see what the Hamiltonian looks like when we pull it back. And we will see it will become non-singular. So H composed phi, we pull it back of Z W. Well, it's 1/2 P squared, so for P we plug in this one. And then we have 1 over Q. So for Q we plug in that square. Okay. So this is W squared divided by 8 Z square minus 1 over Z square. And let's say we want this to be equal to some C. Let's take C equals to minus 1/2 for the fun of it, yeah? So for some negative, actually we want to, so we multiply by 4 Z square, then we get w square over 2 minus, what? I think I want to bring this to the other side, so we get a plus 2 z square is equal to 1. No, not 1. I think I multiplied by 4. Equal to 4. So what do we see here? Now let's, after we replace w by square root of 2w and z by z divided by square root of 2, we get rid of the 1/2 and the 2. This is a symplectic transformation. So then this becomes equivalent to w squared plus z squared is equal to 4. Yeah, after this transformation. So so this we view as a Hamiltonian now, where this is position, this is momentum. So this now is a Hamiltonian on R4. Yeah, so this is some Hamiltonian K of Z and W. What system is this Hamiltonian describing? It's just describing two uncoupled harmonic oscillators. Yeah? So this if we decompose it into the first component and the second component, then it's a sum of two one-dimensional Hamiltonians which are completely independent. Both of them are just harmonic oscillators. So if we look in phase space, they just both move on circles, and together they move on great circles on the three sphere. Yeah. So the solutions are great circles on the sphere of radius 2 in R4, because we have a 4 here on the right hand side. We see the sphere of radius 2 in R4. Yeah? What is the length of these great circles? Will be 4 pi. Yeah? Because it's a sphere of radius 2. Now, and well, first of all, we see this regularizes our system, because now there's nothing bad happening if Z, which corresponds to our original position variables here, if this becomes 0. Yeah? The original correlation was at q equals 0, which is at z equals 0, but nothing bad happens here at z equals 0. It's just going straight through. But now we described it as a flow on the 3 sphere. Now, how does it relate to the Moser regularization? The sphere of radius 2 has a 2-to-1 cover, so I'm almost done, over RP3. When you identify antipodal points in the sphere, you get a 2-to-1 cover to RP3, but RP3 is the unit, I think this was Stefan's notation, the unit cotangent bundle of the 2 sphere. And that is where the Moser regularization lives. Because in the Moser regularization we saw the geodesic flow on the 2 sphere, and this is where it lives. We take the 2-to-1 cover, we see that sphere. And because the 2-to-1 cover, the orbits of here will have length 2 pi. Yeah? And which is what we're seeing, because those are great circles on the two sphere. Yeah, and so we see that the Levi-Civita regularization lives on the sphere S3, and we have a 2-to-1 cover of S3 to RP3, and there we see the Moser regularization. So those two regularizations are related in a nice way, and all this will come up tomorrow and on Friday when I discuss the three-body problem. Then we're going to introduce a third body, but we're going to use the same regularizations to get rid of collisions, and we'll see how useful they are. Okay, thank you very much.
Yeah. You have any questions? Thank you.
You could take a shortcut there when you have your W squared plus Z squared equals 4. You can do the same trick as before with the stereographic projection. You could push the Z over to the other side and divide by it,
Yes.
and then use the Monpintouillet principle to say that those motions are the geodesics of that metric, and that the metric is again the round metric.
Ah, yeah. You could also do that. Yeah. You could do that. Yeah, you could probably. Yeah.
Further questions? And I thank the speaker again. We have 15